Assalamualaikum and a very good evening to all. So today I'm going to continue my lecture on Cohen method. So Cohen method is based on implementation of adaptation of open loop system from the automatic system. So imagine that you have one complete automatic system and then you want to know what is the starting point for the parameters for each controller. So the first thing that you have to do is you have to redraw, or you have to off the controller of the system so that the system turn to manual system. So originally we have this control system, which is feedback control system. This is closed loop. This one I refer to the same problem from lecture notes. I remember that we have transportation lag with delay of one time unit, and then we have a process with second order system. The load I put into the zero because I don't want to put the influence of load to the system. And then we have a controller, of course, here, because this is originally this is automatic system. So to use Cohen to determine the starting point of our value for, let's say, for this example, I will give you the example of KC for proportional controller only. So we need to transfer, we need to convert the feedback control system, which is the automatic, to the open system, open loop system. So if you see here, this is the closed loop and this is the open loop. So what I did is I exclude the existence of controller. Also, I exclude the, what else I exclude here? The summing junction also I exclude, because the summing junction is used to combine the input and the feedback, the output from the system back to the system. So I exclude both, leaving only this. So we look at this open loop system. So now I'm going to give one, I'm going to force the system, the open loop system, with the same final value, which is 10 also, to the system. But now, right now, the system is in open loop. Okay, we have input. I also put the load, but I put 0 there. I remain the summation block here, and also the process transfer function also I maintain to this. The only thing is that the output of the process transfer function is input for the transportation delay, and then back to the output. If you see from the original block diagram, after leaving the process transfer function, after leaving the process, going to the transportation delay to the major element back to the system. But here I put after transportation delay, it goes to the output. Okay, so now it becomes open loop. Okay, so I run the system. Ada dua sebab both simulating, so we exclude this one. Okay, you look at this. So because I put the simulation time up to only 100 time unit, so this is the set point. So this is the output of the system, open loop system. So this is what we call as reaction curve. So this reaction curve is important for us to determine the value of BM, TD, T, KP, which is important for us to calculate the starting point, starting value of KC. Okay, so you simulate, you introduce the input, and then you simulate. You get this graph. Then we want to analyze this graph. So what I did is I edit this graph, and then you know how to edit, right? You go to the edit figure properties. You edit, or you can replot on console or using synods. Okay, so I did that, and I transfer the graph to Words, okay, to Microsoft Word. So this is the enlarged figure. I put up to 70 simulation time, up to 70, and the y-axis is maximum is at 10, minimum 0. So this is the reflection curve. So the first thing is you have to draw one tangent line at the linear, the almost linear curve of the reaction curve. So this is a reaction curve. The almost linear part is here. Okay, so I draw one tangent line that touch to the almost linear curve here. So this is the tangent. I draw a tangent. Okay, I draw a tangent. I enlarge. Okay. So I draw a tangent. So from the tangent, I determine the slope of the linear curve. The slope is S. You can refer to the lecture notes, and also you can refer to the textbook chapter 18. S is equal to y2 minus y1 over x2 minus over x2 minus x1. So y2 is 4 minus 1. So this is your tangent, okay? So we want to calculate the slope, the kecerunan of the curve, because this is linear. So over 7, this is your y-axis, 7 minus 2.8. Okay. I don't have any option here. I just based on the scale that I made manually, because we can interpolate the graph, but I don't want you to be burdened by new command in Scilab. So as long as you get the point or you get the principle, I think you are good to go. So that's why I just draw manually. But this is originally from the Scilab. Okay, so you get 3 over 4.2, and the slope is 0.7142. Okay, this is S. What else can we get from this reaction curve is you get the value of TD. The TD is actually the x-intercept of the linear curve. Okay, 1.5, almost 1.5. Other than that, you identify, you know this already, this M is equal to the set point or the forcing input to the system, to the open loop system. I put 10. You can put any value. Okay, I put 10. Other thing that you have to calculate is T. Okay, T is determined by the value of the steady state, which is 10 over S. S is the slope that you calculated before. This is the value. You get 14. There is other method to determine the value of T, capital T, is by extending the linear curve up to until it intersect with the horizontal line of the input okay, you get the value of 15.4. You minus with the value of the TD, 1.5. You will get 13.9 is equal to 14. So almost the same as the value that you have calculated by using slope value. Okay. These values are important to be used to calculate the value of the controller gain for KC. Okay. And then next to the value of KP, and also you need to identify of course you know the value. Dah tahu dah value. This is the value. BU is actually the value of steady state. Okay, equal to 10. So KP is the ratio between the ratio of steady state to the forcing input. Okay, so 10 over 10, I get 1. Okay. So we have BU steady state. We got already the value of KP, value of T, capital T, M value, S the slope, and also TD. So you use this value to determine the value of KC. So what I did that I use Excel because if you refer to the Cohen setting table, there is several formula to calculate the parameter of the controller according to the types of controller. So for the controller of proportional controller, the parameter is KC. So this is the formula to get the value of KC. So I just use Excel because to make my calculation easier. So I put the value of S determined from the reaction curve, M, BU, KP, T, TD. Okay, up to here I refer to the formula given in the textbook or in on the lecture notes. So I separate the expression so that I can easily calculate the whole equation. So I separate into 1 over KP, T over TD, TD over 3T, and the last one I get the value of KC. Yang ni biasa kot saya rasa because you know how to use Excel. You just put the equation, the formula here. Okay. Also here and here, okay. Or you can just calculate manually using calculator. But I'm not very good of using calculator, especially when you have this mana bracket ni saya jadi lost sikit, jadi saya terlupa nak tekan yang tutup tekan. Jadi I think better I'm using Excel. It's up to you, okay? So the last thing I got is the value of KC. So KC is 9.66 to the power or to the how many decimal point? 1, 2, 3, 4, 5. So I got almost 9.67. Okay. So this value, I need to use that value to you go back to the block diagram. Remember I draw two block diagram. The first one is the closed loop. The other one is the open loop. You get the value of KC is from the open loop. Now we want to implement the value of KC that we have calculated previously just now. You put in this. So 9.66, 9.67 almost. So 9.67. I put a value here, okay, and then I run the system, the block diagram. Okay, this is the output. Okay, so if you get this curve, this is not the end of your simulation, because as I mentioned before, what you get is actually the value of approximated. So you need to fine tune. So you cannot assume that whatever you get from the Cohen must be the same as the value, the same as the Ziegler-Nichols. If you refer to the textbook, chapter 18, there is a slight, there is a difference between the value obtained from the Ziegler-Nichols and Cohen. But it doesn't matter because both are giving you the starting point. After that, you have to further tune or fine tune. So I think that's all. After you get this value, you implement to the closed loop block diagram, and you further tune or fine tune, and then you use the same value to determine the value of Kc and tau I or tau D. You refer to the lecture notes. You only run the open loop block diagram once, only to get the reaction curve, and that value, okay, the same value can be used to determine the other parameters to for another controller, and then you fine tune. The good thing about Cohen is it covers all the controller. Compared to the Ziegler-Nichols, you only have P, PI, and PID. There is no PD. But it doesn't matter. You can use the value of Kc and tau D from the fine tune of the PID and and PI to get the value of PD. Okay. The objective is only to get the starting value or approximated value to further tune your controller's parameter. Okay. I think that's all.